So kinetics is the study of rates of reaction. So how fast or slow do reactions occur? How do we measure that? How do we express and communicate information about that? So that's kind of where our focus is going to be. So the first thing we want to look at is, all right, what has to happen for a chemical reaction to occur? And the basis for this is something called collision theory. And collision theory has three basic parts. It says that in order for a reaction to occur, that the reactants must collide, that the collision has to have sufficient energy, and we've looked at this back in the last unit when we looked at the energy diagrams, and we talked about something called activation energy. So we're talking about that the collisions have to have a certain amount of energy. That's the activation energy for the reaction. And then also, it's that the reactants, when they collide, they have to have the correct orientation. So that just means that the way in which they hit each other, like which end of the molecule collides with a certain end of the other reactant molecule, that makes a difference. So not every collision, even if it has enough energy, will progress to create products. They also have to hit each other in the right way. All right, so this is kind of a little bit of a review, but it's been a couple of weeks, so let's take a look. Here's our energy diagrams, and so we're looking for, we've got potential energy on the Y, and then our reaction coordinate or reaction progress is on our x-axis. So if we look, which represents the potential energy of the product? So we're assuming that this is our 0, and so remember that our products are here, and whoops, what happened there? And our reactants are here. So line E represents the energy of the products, all right? The potential energy of the activated complex. Remember, that's kind of like an intermediate state that is where the reactants have started breaking bonds and the product bonds are starting to form, so it's like an intermediate state, and that is at the top of the hill. So up here, this is our activated complex. And so letter C would be that one, and then the potential energy of the reactants, that would be letter A. The activation energy, that is the energy from where the reactants start up to the top of the hill, up to where the activated complex is formed. And so that's represented by line B. And then the heat of reaction, that's our enthalpy, or delta H, and that's the difference between the products and the reactants. So F represents that amount of energy. And then here, because our products have a higher energy value than our reactants, that indicates that that is an endothermic reaction. Now the reverse reaction, that's if we're starting on the right side and working our way to the left. So essentially our products are now our reactants, and the reactants are now the products. So the activation energy of the reverse reaction is from the products to the up to where the activated complex is, and so that's letter D. And then it says which letter indicates the heat of reaction of the reverse reaction. Okay, so that is still going to be the same because remember our enthalpy or delta H of the reverse reaction is going to have the same magnitude because it's still the difference between products and reactants. It's just that the sign would be opposite. So we're still, letter F still represents the size of that change in energy. And then the reverse reaction, where we're starting, is at a higher energy than where we end up. So that means it is exothermic. Okay. We didn't go over this part in class, but in the event that you wanted to just use this to kind of make sure that you're good to go with these energy diagrams, let's just go ahead and I'll fill in the answers for this. So reactants of the forward energy, it's about 80, and the products is about 160, and the activated complex is right around 240. Activation energy of the forward reaction is 240 minus 80, so that's about 160. The delta H is going to be 160 minus 80, so it's about 80. The forward reaction, again, this one is endothermic. And the heat content of the reactants of the reverse reaction is about 160. And the heat content of the products is around 80. The heat content of the activated complex for the reverse is still 240. The activation energy for the reverse is going to be 240 minus 160, so that's about 80. The heat of reaction, or delta H of the reverse reaction, is going to be, products is 80, reactants is, so products 80 minus 160, so that's going to be a negative 80, and the reverse reaction is exothermic. Okay, so we're going to kind of use these questions to go further into our introduction of reaction rates. So chemical reactions occur when reactants collide. For what reasons may a collision fail to produce a chemical reaction? So remember we said if it has, okay, so, whoops, I don't know why it did that. Not enough energy, or also if it has the incorrect orientation. If every collision between reactants led to a reaction, what determines the rate at which the reaction occurs? Okay, so that means if every collision, so if we did have enough energy and we did have proper orientation, then the rate is solely going to be based on the frequency of the collisions. So more collisions in a given amount of time means we're going to have more reactions. So what is the activation energy of reaction, and how is this energy related to the activated complex? The activation energy, that is the energy needed to get the reaction started. That is the minimum energy that the collision has to have. So if we remember from our energy diagram, so that's going to be this amount of energy right there. And so it's the energy that is required to create that activated complex so that the reaction can go forward. We're going to talk more in detail about catalysts, which is brought up in number 4, but essentially a catalyst, it increases reaction rate by providing a pathway with lower activation energy. Okay, and so that means that more collisions will go forward and create products. All right, so 4 things that will speed up or slow down a chemical reaction. So changing the temperature, because changing the temperature is going to change the kinetic energy of the particles. So changing the temperature will affect the frequency of the collisions and also the energy of the collisions. So raising the temperature, we're going to increase the frequency and the energy of the collision. So that would speed up the chemical reaction. The other thing is the concentration of the reactants. So we can like change the concentration by either adding or removing reactants. Or the other thing that we can do to change the concentration is we can change our volume. If it's gases or if it's, say, a solution, we might change the amount of solute. So that can also change the frequency of the collisions. The other thing we can do is we can change the surface area of the reactants. And by that, I mean that if we, for example, grind the reactants up into a powder, that increases the ability for the reactants to interact with each other, which means we're going to have more collisions. So a greater surface area is going to speed up the reaction. And then the 4th thing, which we mentioned before, is that the presence of a catalyst will also change the rate of the reaction. All right, here's, again, this is just for the review purposes, since we've done these energy diagrams before. But it says we want to draw a energy diagram where it has the energy of the reactants is at 350. So we'll put it up here at 350. It's going to come in like this. It's going to go up, and then we're going to come down, and I'm sure this is not, my scale is not great on this, but that would be 250 for the products. And then if the activation energy is 100, that would put this at the top of the hill at 450, because that would mean I have a 100 between my reactants and the top of the hill. And it says, is the reaction endo or exothermic? It is exothermic because the products are at a lower energy than the reactants. Okay, how could you lower the activation energy? That would be by adding a catalyst. And so let me put, let's do this. So say we're going to use a red line to show if a catalyst is added. So essentially what adding a catalyst will do, all right, is it makes the hill smaller. All right. Note that it does not change the value or the energy of the reactants or the products. All it does is it just affects the size of the hill in the diagram.